So now after the break, we're going to walk a little bit in her footsteps, and we're going to focus on these two lines, which is indeed in the solar spectra, and the reason why this argument was made, right, that the hydrogen is much weaker than the calcium, so there should be much less hydrogen. We will take the opposite approach and show that indeed it makes sense, despite the fact that hydrogen is much, much more abundant, which we know nowadays, than calcium, that it actually, in the solar atmosphere, the H-alpha line, which this is, which we all know now, because we have calculated its rest wavelength. This is a nanometer, so it's 560 angstroms, is weaker. So, okay, 8.4. See how we're going to set this up today. Yeah. So, again, we have seen from our previous exercise that essentially the depth of the depth of the spectral line in H-alpha is essentially proportional to the line extinction coefficient. That's just what we did before the break, right? But the line extinction coefficient then is essentially just the classical cross-section, the oscillator strength, in this case for H-alpha, times the number density of ionization stage 1, excitation stage 2. And then, some line profile function. Now, the of calcium 2, which is then 1 to 2, is then just proportional, this is of course H-alpha, to the line extinction of calcium 2, 1, 2, which is then just this, FLU, calcium 2, 1, to 2. And then it's N in the second ionization stage, first excitation stage, and then the profile function. So you can see that the ratio here, if we assume, which I didn't include, but that F, the oscillator strength, FCL or FLU of H-alpha, is approximately the same as the oscillator strength of calcium 2 of 1 to 2. And that's okay, huh? That's an okay assumption to do. We have calculated the oscillator strength for H-alpha, and I've also told you that, for that we would have to do full quantum mechanical, but luckily, since we're astronomers, we can look that up in databases. That's good for us. So we see that essentially the absorption depth here will be, the line profiles are approximately equal, right? N12 divided by N21, when this is hydrogen and this is calcium. So this is the ratio we need to plot, which is also what makes sense, why this was believed, because the number density, it should be proportional of the number density of the atoms, and since the number density, the calcium line is so much stronger, then okay, the number density of calcium should be much higher. But now we're going to try to calculate this ratio, assuming in the exercise a temperature of 5,780 Kelvin, an electron density, which here is given, but which we, at least for if we assume a hydrogen-dominated plasma, we know how to calculate, right? But here it's given for convenience of solving the exercise. It becomes too massive otherwise. And we have a number abundance of calcium versus hydrogen, total given, And that we know nowadays is, like mentioned also in the video, it's only like 2 parts in a million. So 2 times 10 to the minus 6. Surely that cannot be true. And we have the departure coefficients of hydrogen to be 1/2. No, the partition functions. And we know, of course, for hydrogen, the degeneracies, state S is 2s squared. We have calculated this. We have the setup also, the calcium 2 divided by the calcium 1 partition function, 2.3 divided by 1.32. This we have not calculated, so this is something that, again, for us is just now lookup knowledge. So given in the exercise, the ionization energy of calcium 1 is 6.11 electron volts, and the excitation of calcium 2 when you go from 1 to 2 is 3.12 electron volts. For hydrogen, we have calculated all of this, so there we know. So this gives us a basic picture here, where we have calcium 1, we have calcium 2, and then we have the first excited state of calcium 2. Okay? This is the line that we're looking for, and the excitation here is 3.12. The ionization here is 6.11. For hydrogen, we know we don't have several ionization stages. We only have neutral hydrogen, and then we have ionized hydrogen up here. This we know from their Bohr atom is 13.6 electron volt. We also have calculated the distance between the ground state, the first state here, 1, 1, and 1, 2 there, and that's 10.2 electron volts. We could repeat those with the Bohr atom, of course. In this case, we would denote this here as 2, 1, right? And this as 2, 2. Okay, so let's now look at this ratio between the ground states. So N, what do we have? N, 1, 2, do I take that? I took it like that, so I'm going to follow, of calcium 2 divided by N1, 2 of hydrogen, okay? So we can just first expand it in terms of just N total of calcium, okay, times, of course, N total of calcium, and then we just divide N total of hydrogen, and then what do we have left? N total of hydrogen divided by, which one did I forget? N1, 2, H, okay? Of these, we can see that this one is already given. It's our abundance. It's 2 times 10 to the minus 6, right? That's what's given that. That's the total. So the ones we need to calculate now are these two, okay? Another way to put this is that in order for the calcium, this is essentially our profile. So in order for our ratio, in this case, we should call it, yeah? So in this case, if we want our ratio to be greater than 1, you can see that the ratio We have 2 times 10 to the minus 6. And then we have N to 1, calcium 2, divided by N tot calcium, right? And then we can just put this downstairs if we want. So that just goes down. Huh? So that's just N1 to H divided by NH tot. So that actually has to be higher than 10 to the minus 6. So the relative fraction of calcium atoms in the ground state of the first ionization state has to be more than 1,000,000 times the relative fraction of hydrogen atoms in the first excited neutral state. So let's start with hydrogen. N1, 2, H divided by N tot H. That's N1, 2, H, H1 plus NH2, so neutral ionized of H, of course, which you then can just write N to H divided by NH1, 1 plus NH2 divided by NH1. All right. So now, in order to do this analytically, we can do another assumption, and that is that the total abundance in H1 is just approximately N11 plus N12, and then we neglect the rest of the terms. So really here, there should be plus N13 plus N14, etc. But as we discussed, because of the Boltzmann factor, we could do this calculation, of course, but we know that because of the influence of this exponential Boltzmann factor, the populations in the excited states are typically much smaller than those in the ground state. So we neglect these. Then you can see that the ratio here becomes N1 to H divided by N1, 1. I will skip the H's all the time. It's hydrogen all the way here, so hopefully we will. It's just, yeah. Okay? And this we can write as, if we bring out that factor, it's just A divided by 1 plus A, 1 plus B, where I've just defined two fractions here, as you can see, for a simplicity of notation. And hopefully the reason why I've just taken out those fractions is it's already clear to you, because A is N12 divided by N11. But that's just our Boltzmann. And B here is NH2 ionized NH1. That's just our Saha. Okay? So the only thing we need to do is to solve the Boltzmann and the Saha, and then we're there. All right, so A. This we know, G12, we look it up in the lecture notes, G11 e to the minus delta E excitation energy, where delta E indeed is 10.2 electron volts. Okay? And G12 we have is just 2 times 2, 2 is 8, yeah? G1 is 2. And then we plug this in, and I pre-did that, so here is, of course, where you are similar on the exam, you will have to do some work with plugging in the right numbers and getting the units correct and stuff like that. But if you do, you should verify this when you get home. You will get 5 times 10 to the minus 9. And again, this is a reflection of the exponential in the Boltzmann factor, as we have talked about before. For the B factor, that's just the Saha relation, right? So I will write down the Saha relation here. We, of course, have it. OH2 divided by the number density of electrons, H1, and then remember we had this thing in the parenthesis, which was essentially 2 pi something something me kt divided by h squared, 3 1/2, and then e to the minus delta e kt, where important delta e now is the ionization energy, of course. It's 13.6 electron volt. But since we were given the number density, yes? $10.2. This one you mean? $10.2. This 8 times, sorry, times. This is the degeneracy. Remember that the degeneracy of hydrogen was 2s squared for a state s. Yeah? So ground state of H alpha has state 2, right? So 2 times 2 to the power of 2 is 8. Yes. So that was just me sloppy handwriting. Sorry for that. Similarly here, you can see that we have all these because we were given the number density of electrons. Yeah. Again, if we were to assume that hydrogen actually dominates, we could calculate that, but that would be the full exam, or that would be like the full week. But one could. One can simply put it in a little program at least. Then in this case, this comes out as 8 times 10 to the minus 5. What does this say? Well, it says indeed what we have had before, that hydrogen is actually in the solar atmosphere, around 600 Kelvin, mostly neutral. All right, and now I erased my ratio. That was not very clever on me. But I had that N12 divided by N tot of hydrogen was, in this case, A, 1 plus A, 1 plus B. But we have seen that A and B all are very, very small. So that in our exercise, this is just A, which is just 5 times 10 to the minus 9. So indeed, the number densities that is in the excited first level is extremely small. You can, of course, plug in the exact numbers here, but since one is 10 to the minus 9, one is 10 to the minus 5, they hardly add to the nominator here. So this is just 1 times 1. And then you just have the A in the beginning. All right. Now we're going to do it for calcium. For calcium, too, but we're interested in the ground state of the second. Okay, so we start as before, but now N to 1 divided by N in calcium 1 plus N in calcium 2. Okay, so here you see that I've assumed that all calcium is either in the neutral state or first ionized state. Okay. Again, we're going to do the same assumption for, in this case, calcium 2, that it is, because we're interested in calcium 2 here, right? That is either in the ground. Yes? it means that you're in calcium 2 here, but you're in the ground state. So you're in the second ionization state, or firstly ionized state, so ground first, and in the first state, so in the ground state. This is the ionization, this is the excitation. So the excitation means that you're in the ground state. The ionization means that you have lost one of your electrons. Yeah? So in this case, we're just writing this as N21 calcium 2 divided by, well, we can take another, then N calcium 2, and then we have N calcium 1, N calcium 2 plus 1, right, in the denominator. We're making the same ansatz as we normally can, counting just in the ground state of calcium 2, so 2, 1, that's this one, plus then of calcium, plus N2 of 2, first excited state here, which will be to the state where we're interested in the line of calcium 2. And then plus this, which is N calcium 1, N calcium 2 plus 1. All right. You see that we get a very similar shape as before. Now, if we take this out, we can take out N calcium 2 there, then we just get the 1 in there, and then we get 1, and then a ratio which I will call C. And here I will call the ratio 1 over D plus 1, where D then is our number density of calcium 2 divided by number density of calcium 1. C now is N2 of calcium divided by N2 1 of calcium. So completely analogous to hydrogen, we have that what we need to solve here is 1 for Saha and 1 for Boltzmann. Okay? So C is just the degeneracy to 2 for calcium now, degeneracy to 1 for calcium, times e to the minus the excitation energy of calcium. And these were all given in the beginning. So if you go back a few blackboards, if I had a smartboard, I could do it, but I can't. Then we would see the numbers. You should have them in the notes. You also have them, of course, in the exercise. Yeah? You plug this in. You will get 4 times 10 to the minus 3. So again, you see that the ionization in the first excited state there is much lower than in the ground state, as usual. Not as much as hydrogen, though, and that you can see the reason if you look at the ionization potential. It's actually lower than for hydrogen, quite a bit, huh? The excitation potential. Now, for Saha, which we do the same as for hydrogen, so I'm just going to leave it here, actually. Okay? This is just the Saha, but for calcium 2 to calcium 1, again, you were given the degeneracy, the partition function in the exercise. You were given the ionization potential in the exercise, and you were also given the electron number density in the exercise. So this, once you have set it up correctly, is just to plug in the numbers, keep the units correct in your head, whatever units you want to work with, and get to the answer 960 or 1000. if we approximate it. So this is vastly different. This means that for every neutral hydrogen, for every neutral calcium atom, there are 1,000 firstly ionized ones. So that means that opposite to hydrogen, which was mostly neutral in the solar atmosphere, calcium is mostly firstly ionized. That's the dominant ionization stage. And that's indeed then, we can already say, okay, but that's why this line is so strong, right? Because it goes from the first ionization stage, the ground state, to the first state. The resonance lines of singly ionized calcium. So, if we put this back into our equation for the number density of 2, 1 calcium, 2 total of calcium, we had it there, 1 plus C, 1 divided by D plus 1. But there you see that D is actually 10 to the 3, right? So this will basically vanish. C is 10 to the minus 3. Well, this will also be 1 then. So this is going to be on the order of 1. Technically, I think that I got 0.995, but that's not going to matter for the conclusion. So what have we calculated? Well, we have calculated that in principle, all calcium that exists in the solar atmosphere, at least to a 99% level, resides in the ground state of calcium-2. And indeed, this is why the line is so strong. Whereas for H-alpha, what we're looking at is a situation where almost no hydrogen is in the first excited state. Thus, we can see that we have the two ratios at hand somewhere here in this mess. Yeah, up there. The ratio, we had our number densities of calcium, which we have calculated to be approximately 1. We had the abundance of calcium, 2 times 10 to the minus 6. And then we had the total hydrogen over NH2, which we calculated to be 1 divided by 5 times 10 to the minus 9. So 5 times 10 to the minus 9. And indeed, this is much, much greater than 1. 3 orders of magnitude in this particular simplified calculation. So that is indeed how we have shown that in the solar spectrum, the calcium-2 line should be much stronger than the H-alpha line. It has to do with the Sahn-Boltzmann relation and the number of atoms residing in the ground state of the relevant transition. And indeed, if you reverse engineer this, it's just what Cecilia Payne did in order to get to the conclusion that we started with, namely calculating these ratios and seeing that, you know, in order for this to make sense, calcium has to be only 1 million part or so as abundant as hydrogen.